Picture the cabin of JetBlue Flight 1230. It's October 30th, a standard run from Cancun to Newark. Passengers are likely, dozing off or scrolling through their phones, trusting the absolute routine of modern flight. Then, without any warning, the plane doesn't just shake, it drops. A sudden, uncontrolled descent that throws passengers against their seatbelts, injures multiple people, and forces a white-knuckle emergency landing in Tampa.
It's the kind of mid-air nightmare everyone fears but assumes won't happen to them.
Exactly. And so naturally, when the FAA investigators stepped in, you'd expect them to find a mechanical failure or maybe a pilot error. But what they found was infinitely more bizarre. The culprit wasn't a broken part or a tired human, it was the sun.
Right. Specifically, strong solar radiation had silently corrupted the critical data inside the plane's flight control computers, tricking the machine into diving.
But here's where the story shifts from a single scary flight to a global crisis. That one incident revealed a flaw so deep that it has triggered the largest recall in Airbus's 55-year history.
We're talking about the A320, the absolute workhorse of the skies, suddenly paralyzed by something as abstract as cosmic rays.
And just weeks after Airbus celebrated finally overtaking Boeing as the world's top manufacturer, they are now scrambling to fix 6,000 aircraft, while airlines from Japan to Colombia cancel flights en masse. It really makes you wonder, how fragile is the advanced technology we rely on if an invisible force from space can bring half the world's fleet to a grinding halt?
It's not just astonishing. I mean, the speed and the severity of the regulatory response clearly shows how seriously the aviation world views this threat.
Oh, absolutely.
Following that JetBlue incident, both the European Union Aviation Safety Agency, EASA, and the U.S. Federal Aviation Administration, the FAA, immediately mandated the grounding and repair of approximately 6,000 Airbus A320 family jets worldwide.
6,000 jets, and we're talking about the A318, A319, A320, and A321, the entire narrow-body workhorse family.
The whole family.
That number it provides the context for the significance of this. It affects over half the global narrow-body fleet. This wasn't a localized issue. It was a global, mandated scramble for every airline that operates one of these jets.
Exactly. The sheer scale is what makes this grounding historic. To put it in context, this is one of the largest safety recalls in Airbus's history, stretching back over 5 decades.
And the timing, as you said, it adds this layer of bitter irony.
It really does. The A320 family had just recently surpassed the Boeing 737 as the most delivered commercial jet. Airbus was riding this high tide of dominance, and then suddenly that triumph was completely overshadowed by a crisis rooted in digital integrity, a single uncommanded event that jeopardized thousands of flights.
Okay, let's unpack this technical problem, because this is where the physics in space meets the precision of flight. We need to identify the specific system that was struck and then define the mechanism of failure. What piece of hardware was the ghost in the machine haunting?
The primary culprit system identified was the Elevator and Aileron Computer, or ELA. For those unfamiliar with the A320, the ELS is absolutely core to its design philosophy. The A320 really pioneered the fly-by-wire system in mainstream commercial aviation.
Right. So unlike older planes, the pilot's commands, the movement of the side stick, they don't directly manipulate hydraulic controls.
Exactly. They are routed through the ELS, which interprets those commands, along with inputs from the flight envelope protection system, and then it physically controls the aircraft's pitch using the elevator and its roll using the ailerons.
So when JetBlue 1230 pitched down uncommanded, it wasn't the pilot doing it, nor was it a physical cable snapping. It means the ELS received a corrupted piece of data, a phantom command, and decided all on its own to initiate that dive. Now, we have to drill down into the microscopic level to define the physical mechanism at play, the single event upset, or SEU.
An SEU, which engineers will often call a single event error, or C, is fundamentally a microscopic physical phenomenon. It's defined as a transient change of state in a microelectronic device.
So like a memory chip.
Exactly. Picture a memory cell holding a single bit of information, maybe a go-up. A particle strikes it, and the resulting charge momentarily flips that bit to a 1.
So it's a data corruption event, not permanent hardware failure.
That's why we call it a soft error. The hardware itself is fine, it remains intact, but the data it holds for that single instant is wrong.
A single particle, flipping a single bit, leading to a catastrophic dive command for a multi-million-dollar jet carrying hundreds of people. That feels almost impossibly fragile. Where on Earth, or I guess, above Earth do these particles come from with enough energy to cause such havoc?
They originate from the cosmos. We are primarily talking about high-energy galactic cosmic rays and solar energetic particles. When these primary rays, which are often protons and heavier nuclei, collide with nitrogen and oxygen atoms in the Earth's upper atmosphere, they don't stop.
You create a reaction.
They create massive cascading showers of secondary radiation. And the most relevant component of this secondary shower for avionics is high-energy neutrons.
And neutrons are neutral, which means they can penetrate materials far more effectively than charged particles, right?
Precisely. And this is the critical point for aviation safety. At normal cruising altitudes, say 30,000 to 35,000 feet, the atmosphere offers significantly less shielding.
So we're more exposed up there.
Much more. The neutron flux, which is the density of these highly penetrating particles, is estimated to be about 300 times greater than what we experience at sea level.
300 times. So every flight is essentially cruising right through a dense neutron shower that's powerful enough to momentarily flip bits in the most critical flight control computers. That context changes everything about how we perceive routine air travel safety.
It does. And this vulnerability isn't exactly new, though its severity increases with modern electronics. SEUs were first characterized back in the 1950s and 60s in the context of space electronics and nuclear testing environments.
Right.
But commercially, the aviation world has known this threat was present for years.
Which brings us to the famous prior incident, Qantas Flight 72.
Yes. That violent aircraft upset occurred in 2008. The Qantas A320 was flying from Singapore to Perth when, suddenly, the plane executed two severe uncommanded pitch-down maneuvers. It was brutal. Passengers were thrown to the ceiling, resulting in multiple serious injuries.
And the investigation found no mechanical or pilot error there either.
None. The Australian Transport Safety Bureau, the ATSB, concluded the most probable cause was a latent software flaw that allowed an intermittent data spike, an anomaly almost certainly caused by an SEU, to corrupt the system and issue a false angle of attack reading.
Wait, okay. If the Qantas incident happened over 15 years ago and investigators suspected the exact same mechanism, a cosmic ray hitting a computer chip, how did we end up with the same fundamental flaw causing the JetBlue grounding now?
That is the central, deeply unsettling question this JetBlue grounding raises.
It feels like the solutions put in place after Qantas 72 failed.
Well, Qantas 72 did lead to immediate software revisions and updates across the A330 fleet to better filter out those anomalous data spikes. However, the A320 incident suggests that the continuous drive toward miniaturization, combined with software updates, created a new vulnerability window.
A new hole in the safety net.
Essentially, yes. The original fixes might have been fleet-specific or simply weren't robust enough to handle the increasing sensitivity of the next generation of microchips being installed across the A320 family.
So the technical challenge here is not static. It's a perpetual race against an invisible, pervasive, and evolving threat that increases drastically the higher you fly and the smaller you make your electronics.
Exactly. It forces us to ask, how do you design avionics to be so robust that a data error from a subatomic particle strike can be reliably recognized, ignored, and mitigated, especially when that corruption happens within milliseconds and can mimic a legitimate control input?
That brings us squarely into the engineering challenge. How do we design electronics to survive the invisible saboteur? Let's talk about the risk profile of modern avionics, because I think a lot of people assume newer technology automatically means better safety margins.
The reality is that in terms of radiation vulnerability, the opposite is often true, especially in the pursuit of greater efficiency and speed. The continuous aggressive drive toward chip miniaturization is a huge factor here.
Why is that?
As chip feature sizes shrink, we're talking well below 100 nanometers now, the amount of electrical charge required to represent a single binary bit also decreases significantly.
Less charge means less margin for error.
Precisely. A tiny particle strike is more likely to deposit enough energy to cause an SEU, to flip that bit of data. The components have become hypersensitive, sitting right on the edge of instability.
And then this inherent physical fragility is overlaid onto massive system complexity.
Right. And as systems become more complex, the number of critical high-consequence locations where an SEU can land, like within the ELAC firmware or the flight control data registers, it just increases.
The A320's reliance on fly-by-wire makes its software integrity not just important, but absolutely paramount to the aircraft's variability to fly safely.
That is the core risk equation. An SEU in a simple system might cause a recoverable glitch. An SEU in a deeply complex embedded system, especially one running sophisticated flight control laws, increases the probability of a catastrophic system failure exponentially.
And Airbus knew this.
Oh, yes. Airbus itself recognized the dire consequence, stating officially that if this flaw was uncorrected, it could lead to uncommanded elevator movement that might result in exceeding the aircraft's structural capability.
Exceeding the aircraft's structural capability. That's the phrase that validates the emergency grounding. That is, the manufacturer admitting the flaw could rip the wings off the plane.
It absolutely justifies the immediate response from EASA and the FAA. It's a level of risk the industry cannot tolerate. Now, we know manufacturers are required to design electronics to be robust against SEUs through multiple layers of mitigation.
Okay, what are those layers supposed to be? We often hear about redundancy in aircraft.
The standard playbook involves two main strategies. First is hardware and software redundancy. For example, having 3 separate flight control computers running in parallel, often with software written by different teams using different programming languages, we call that dissimilar redundancy.
So if one computer gets a bad command, the other 2 can outvote it.
That's the idea. The second is error-correcting code memory, or ECC memory, which uses parity bits to automatically detect and correct single-bit flips caused by these soft errors.
But the fact that the JetBlue incident occurred and that it led to a fleet-wide grounding means that both of those safeguards, the redundancy and the ECC, were somehow defeated or bypassed by this new software.
That is the frightening implication. It suggests either the SEU occurred in a memory area that wasn't protected by ECC, or, more likely, the corruption occurred in a piece of transient data like an immediate command register or a buffer, where the error was immediately acted upon before the triple redundant system could definitively recognize it as an outlier and shut it down.
So the vulnerability was like an accidental bug introduced in a recent software revision.
It appears so. A hole inadvertently punched in the safety net.
So the safety failure wasn't due to aging parts or metal fatigue. It was a digital hole created by programming change. This leads us to the solution dichotomy: the quick digital fix versus the hard physical problem.
For the vast majority of the global fleet, about 5,100 aircraft, the fix was deceptively simple: a software rollback or an update.
Just a digital patch.
Exactly. It takes a relatively short time, maybe 2 to 3 hours per aircraft, which can often be managed during overnight layovers. The speed of the fix confirmed that the vulnerability was tied to a specific, recently introduced software state.
That sounds manageable for operators. But then you have the hard problem, the group that needs more than a digital patch.
That's the remaining 900 older A320 models. These jets require physical hardware replacements specifically for the internal computing boards within the ELAC units.
And why is that?
Because the older hardware architecture simply couldn't support the updated radiation-hardened software patch that was developed for the newer models. They needed a complete physical swap-out.
A physical swap-out across 900 jets creates an immediate crisis for the supply chain, doesn't it? You can't just, call up your local distributor and ask for a pallet of highly specialized flight control computers.
Absolutely not. This turns a routine software fix into a complex logistical nightmare. You have immense supply chain bottlenecks, especially for components as specialized and highly regulated as flight control computers.
And this is on top of existing industry problems.
Right. It's amplified by pre-existing issues.
Yeah.
Global scarcity of aircraft parts, maintenance backlogs already straining repair shops, and critically, a severe labor shortage of qualified avionics technicians worldwide.
So an airline might have the new ELAC unit ready, but if they don't have a certified technician available to perform the complex installation and calibration, the plane stays on the ground.
Precisely. What should have been a simple few-hour software job for the entire fleet turns into prolonged downtime, potentially measured in weeks or months, for those 900 older aircraft.
And this is really forcing engineers to rethink the way they test and certify avionics. If cosmic rays are the threat, we need to mimic cosmic rays here on Earth in a controlled, certifiable environment.
This is where accelerated testing and specialized facilities come into play. The incident exposes a clear and present gap in current aircraft certification processes regarding atmospheric radiation resilience. You can't fly a chip for thousands of hours to wait for an SEU, so testing needs to simulate that exposure instantly.
The goal is accelerated testing then.
That's right, simulating thousands of hours of flight time in just a few hours of beam time. We've had specialized facilities for decades, like Lancy in the US and Triumph in Canada, which use particle accelerators to create intense neutron beams for testing. But the engineering challenge now is precision making these simulated environments perfectly match the actual threat spectrum.
Why is achieving that precise match so important?
Because not all neutrons are created equal in terms of their effect on chips. Older testing often used high-energy approximations, but modern, highly miniaturized chips are increasingly susceptible to lower-energy neutrons, specifically the thermal neutrons that can interact with semiconductor materials.
And cause reactions that flip bits.
Exactly, particularly with boron atoms sometimes used in doping. So the testing needs to match the exact profile of the atmospheric radiation the plane flies through.
And this is where new projects come in.
Yes. This is where the UK's CHIP-I project, part of the ISIS neutron and muon source, is so significant. It represents the next generation of accelerated testing. The key goal is to precisely match the specific atmospheric neutron spectrum, which is mathematically described by the QARM model.
Tell us more about the QARM model. Why is matching that spectrum a fundamental leap forward?
The QARM, or Quality Assurance Radiation Model, provides a high-fidelity benchmark for the flux and energy distribution of secondary neutrons at cruising altitude.
So it's more accurate than what they used before.
Much more. Previous test standards used generic high-flux beam profiles that were good enough for initial component hardening, but they didn't accurately represent the complex distribution of high-energy, mid-energy, and low-energy neutrons found in the atmosphere.
So by matching the QARM model, CHIP-I can find vulnerabilities across the whole spectrum.
Exactly. It ensures comprehensive protection, especially against those lower-energy thermal neutrons that become problematic with sub-100 millimeter feature sizes.
That's a huge distinction. It's moving beyond just high-intensity testing to highly accurate spectral testing. What else makes CHIP-I unique compared to the existing older facilities?
Beyond the precision beam, CHIP-I offers a revolutionary concept, the large flood room.
A flood room? What exactly does that achieve?
Well, current facilities typically use a highly collimated, narrow pencil beam to test individual components or small circuit boards. This is fine for component certification, but modern aircraft systems are servers running complex integrated software.
So it's not just about one chip failing.
Right. An SEU might not cause a failure by itself. It might only cause a crisis if it happens alongside another SEU or if it defeats error correction. The flood room addresses this by allowing for the testing of entire systems. We're talking whole flight control computers, networking servers, or radar systems with an isotropic or uniform neutron flux that washes over the entire system simultaneously.
So instead of testing a single memory chip in isolation, they're testing the entire box that houses all the memory processors and communication bus, making sure the system as a whole handles the error gracefully.
Exactly. This allows designers to verify system-level resilience, how the redundancy managers handle simultaneous or near-simultaneous bit flips, how memory controllers react, how different computing elements interact under stress. The industry recognizes that neutron seas are an increasing problem, and designing resilient modern avionics demands this holistic, system-wide testing approach.
That is fascinating. It shows how the threat of a single particle has shifted the entire methodology of high-reliability system engineering.
Indeed. The pressure is on. The A320 grounding provides the perfect, sobering case study demonstrating why this investment in testing infrastructure, like CHIP-I, is absolutely essential for the next generation of fly-by-wire aircraft.
The theoretical physics and engineering challenges are one thing, but the immediate reality of this grounding played out in the global logistics system, and the timing could not have been worse. Let's shift now into the global impact, starting with the operational chaos during peak travel.
The timing was truly brutal. The grounding mandate dropped right during the U.S. Thanksgiving holiday travel period, which is arguably the busiest, most high-stress period for air travel in North America.
Which just compounded the impact exponentially.
It turned a technical glitch into a mass operational catastrophe across continents.
The disruption was immediate and widespread. We saw airlines scrambling everywhere to comply with the emergency directive while trying desperately to manage passenger flow during a holiday rush. Let's look at some specific examples, starting with the largest operator of the affected jets, American Airlines.
American Airlines had to tackle a massive task. Initially, 340 of its 480 A320 family aircraft required urgent updates. Think about that. 41% of their narrow-body fleet suddenly pulled from service during their peak demand period. They had to execute a rapid-fire maintenance marathon, diverting resources, repositioning crews, and working with regulators literally by the hour to get planes inspected, patched, and returned to service.
And the chaos wasn't limited to North America. The disruption rippled across major emerging markets.
Absolutely. Indigo in India, which operates one of the world's largest A320 fleets, was reported to be the second most affected carrier globally. Their operational flexibility was severely strained.
And in Japan.
Look at Japan. ANA Holdings, which runs the largest Airbus narrow-body fleet in that country, canceled 65 to 95 domestic flights over a single weekend. That affected approximately 13,200 passengers. For Japanese aviation, which prides itself on punctuality, this was a significant hit to their reliability.
In Latin America, the operational freeze for some carriers was almost total.
Take Avianca in Colombia. They had about 70% of their fleet, roughly 100 aircraft, affected by the grounding. The severity of the mandate meant the disruption was so immediate and severe that they were forced to suspend all ticket sales for the affected routes through December 8th.
So a complete operational paralysis.
They couldn't risk selling tickets for flights they weren't sure they could legally or safely operate.
That level of operational freeze due to a single software command error is staggering. And there was that anecdote that captured the real-time confusion in the cockpit, what we called the pilot's pause.
Yes, the Finnish-Finnair delay. A passenger noted that their flight was delayed almost an hour, not because of a mechanical check or bad weather, but because the flight crew had to stop and verify, using digital documentation and communications with maintenance, that they were operating a stable, compliant software version before they could legally taxi.
So it wasn't a quick check.
Not at all. It was a complex process of regulatory confirmation on the tarmac, illustrating the instantaneous high-stakes chaos the emergency directive caused in every cockpit worldwide.
And while those planes sat waiting for verification or a physical replacement, the pressure shifted entirely to the human element, the ground crews, locked into what we call the hangar marathon.
The human cost and logistical pressure were immense. Engineers at carriers like Air India publicly confirmed they were working day and night, literally round-the-clock shifts, to comply with the mandated deadline to get their 138 affected planes fixed. They weren't just fixing a flaw, they were fighting the clock and the pre-existing system constraints.
They were already dealing with the industry-wide headache of labor shortages and existing maintenance backlogs.
Precisely. And then suddenly, they get a fleet-wide, time-sensitive emergency software patch requirement dropped on them during the busiest travel week of the year.
Which means diverting resources from scheduled maintenance, incurring significant overtime costs.
And potentially delaying essential non-urgent maintenance on other aircraft simply to comply with the immediate A320 grounding order. It turned a technical software bug into an intense human endurance challenge fought inside hangars globally.
It's time to talk about the dollars and cents behind this chaos, the staggering financial fallout.
The costs are immediate, enormous, and multi-layered. Industry estimates suggested the daily losses from cancellations, rebooking fees, crew repositioning, and passenger compensation were in excess of $100 million globally.
$100 million a day.
That is the cost of systemic disruption during peak travel.
And we have to consider the punishing cost of an aircraft on ground, or AOG, incident itself, even if the plane is just sitting there waiting for a 2-hour software update.
The AOG costs are often obscured, but are critical to understanding airline profitability. Depending on the aircraft type and the route it was scheduled to fly, grounding a plane can cost between $10,000 and $150,000 per hour.
Per hour.
For a major international flight, the loss of cargo revenue alone can be tens of thousands of dollars. When you multiply that across 6,000 aircraft, even if most are only grounded for a day, the cumulative cost to the global industry runs into the billions.
Amid this crisis, the financial markets had a very mixed reaction to Airbus. The core business looked strong, but the integrity of their product suddenly looked vulnerable.
The optimism stems from Airbus's overwhelming fundamental strength in the market. Analysts like JP Morgan and RBC Capital actually upgraded Airbus's price targets during the crisis.
Really? Why?
They cited two factors: strong Q3 earnings that demonstrated robust current performance, and a record order backlog. We are talking about 8,754 commercial aircraft on order, effectively locking in years of production.
That order book signifies overwhelming structural demand that a single safety issue, even one this large, cannot immediately erase.
Exactly. One discounted cash flow model suggested the intrinsic share price should be significantly higher, around 330.69, suggesting that despite the media crisis, the company was fundamentally undervalued long-term due to that massive locked-in order backlog.
But the immediate technical failure clearly gave other investors a pause, leading to caution.
Yes. Other analysts downgraded the stock to hold. The grounding reignited concerns about broader operational and financial challenges that pre-existed the cosmic ray incident.
Like engine supply delays.
Right, which constrained the delivery of new aircraft and negative free cash flow that Airbus had reported in the first half of 2025. The incident, therefore, served as a stress test, highlighting that while the sector's long-term resilience is strong, the oversight regarding non-traditional risks like radiation vulnerability and supply chain fragility is dangerously inadequate.
So investors are asking a core question. Can Airbus manage its impressive growth and order book while simultaneously dealing with these complex digital and logistical vulnerabilities that hit during peak travel periods?
It forces a shift in investor focus. It moves the conversation away from just production rates, how many planes can you build, and onto the risk management framework of aerospace firms. How well can you ensure the digital integrity of the planes you sell, and how quickly can you execute a global recall when necessary?
And the latter is clearly where the vulnerabilities lie.
Yeah.
Let's zoom out further. The A320 grounding isn't just a crisis for Airbus or the airlines that own the 900 older models. It's a symptom of deeper systemic issues across the entire aviation industry, particularly for legacy U.S. carriers.
That's the critical, bigger picture takeaway. The software flaw was the initial trigger, but the resulting chaos was amplified dramatically because of pre-existing operational fragility within many older fleets.
For legacy U.S. airlines, many are operating fleets with an average age of over 20 years.
Exactly. And these aging aircraft are inherently more prone to maintenance issues, corrosion, fatigue, and structural problems, regardless of the sophistication of their fly-by-wire system.
And post-pandemic, the reliability of these older fleets seems to be deteriorating significantly, making them less capable of absorbing external shocks like this A320 grounding.
The data is stark and concerning. Technical dispatch reliability, the ability of a plane to be ready to fly on schedule, has declined by as much as 50% post-pandemic across certain legacy fleets.
50%.
And maintenance-related cancellations have surged 2- to 3-fold. This isn't just bad luck. It's a confluence of aging hardware that requires more attention, parts scarcity exacerbated by supply chain disruptions, and a chronic labor shortage of experienced mechanics and technicians.
It sounds like the airline industry is caught in a debilitating financial trap. Why do carriers keep flying these older aircraft if they're so maintenance-intensive and operationally fragile?
It's a classic but flawed economic calculation. Replacing an aging fleet is massively expensive capital expenditure. A new wide-body jet can cost upwards of $200 million.
So they're trying to defer that huge upfront cost.
There's a strong short-term economic incentive to extend the lifespan of older models as long as possible.
But what are they paying for that short-term saving?
They are paying heavily in long-term operational fragility. While they save on the $200 million acquisition cost, those older planes can rack up between $100 million and $200 million annually in lost revenue, compensation, and increased maintenance costs due to failures.
So they're swapping large one-time capital expenses for chronic, escalating operational expenses and reputational damage.
Operational fragility is the perfect term. When a carrier like American Airlines, which was already struggling with maintenance backlogs, suddenly loses 41% of its A320s to a mandatory grounding, the system rapidly approaches paralysis. There is zero operational flexibility left.
The incident forces a necessary but uncomfortable shift in regulatory focus. We need new design standards that explicitly account for threats outside the realm of traditional mechanical engineering.
Absolutely. This incident mandates a fundamental new look at international aviation safety regulations and aircraft certification processes. Regulators EASA and the FAA must now significantly enhance their scrutiny of critical flight control systems against non-traditional environmental factors like solar and cosmic radiation.
Historically, safety focus was on things you could see, touch, or measure mechanically. Fatigue, cracks, metal failure, hydraulic leaks. Now safety hinges entirely on digital integrity.
It's a paradigm shift from mechanical trust to digital verification and proactive software resilience. We are learning that the most sophisticated parts of the aircraft are the ones we must trust the least without constant proactive digital validation.
What does this systemic vulnerability mean for the future of investment in the airline industry?
It serves as a clear, urgent, cautionary tale for investors and management teams globally. Airlines that continue to rely on short-sighted cost-cutting measures that exacerbate long-term systemic vulnerabilities, like neglecting fleet modernization or failing to invest aggressively in data-driven predictive maintenance technologies, will face escalating costs, heightened safety risks, and severe reputational damage.
The market and regulators will increasingly favor those carriers that proactively manage these complex risks.
Through aggressive modernization and resilience planning, yes.
This entire deep dive has been a remarkable journey into fragility, revealing 3 deeply interconnected layers of vulnerability in modern aviation. We started with the microscopic physics of the single event upset, a single ionizing particle flipping a bit in the ELEC computer, a technical failure that had been previously suspected in the Qantas 72 incident years ago.
And that invisible microscopic failure triggered a massive operational and economic disruption. It grounded 6,000 aircraft globally right at the peak of the Thanksgiving travel season, forcing airlines to absorb over $100 million in daily losses and exposing severe existing logistical problems like labor shortages and supply chain fragility.
And finally, this all highlighted the structural safety vulnerability of modern fly-by-wire technology, demanding a complete overhaul of how we test avionics. It is pushing engineering toward next-generation facilities like ChipRR, which must test entire systems against the atmospheric radiation threat using high-fidelity models like QARM, ensuring we move from reactive maintenance to proactive digital resilience.
The industry now faces the clear mandate that in an age of digital dependence, safety assurance must be redefined to account for forces that are literally out of this world.
The most profound insight from this global scramble is the realization that in our pursuit of increasingly advanced software-reliant technology, we have inadvertently made our most sophisticated machines susceptible to the most ancient, pervasive, and untamable force in our solar system, the sun.